Hello, everybody, and welcome back to Geology 109, Evolution of the Earth. For week 2, we are going to be starting out with chapter 2, looking at floods, fossils, and heresies from your Prothero and Dot textbook of Evolution of the Earth. So I want to look at a couple of different topics this week, notably an introduction to stratigraphy and the fundamental principles of geology. We're also going to take some time and look at the founders of historical geology. It's important to note where some of these ideas came from, and even sometimes exploring ideas that were wrong so we don't make the mistake of making those errors in the future. We're also going to look at the differences between catastrophism and uniformitarianism. These are ways in which we describe changes in the Earth over time. And finally, we're going to end up looking at fossils, different types of fossilization, and the importance of the fossil record to historical geology. So first, let's start out with a little bit of a discussion on stratigraphy. So what exactly is stratigraphy? Stratigraphy is a subfield of geology that looks at the study of the layering of strata or sedimentary beds. So in lab, over the last week or two, we've been looking at different types of rocks and minerals, but we talk specifically about sedimentary rocks. Sedimentary rocks represent ancient environments, and if we're lucky, also include and contain remains of the organisms that were living in those environments millions of years ago. So the fossils that we have contained within these strata represent the life that was inhabiting these ancient environments. So if you come across a sandstone, that could possibly be a beach deposit, or it could be a river channel, or it could be part of a desert. All of these have organisms that live in them, these types of environments, and the fossils contained therein thus represent that. Stratigraphy is a really important aspect of geology and paleontology because this is really the time context by which we're finding our fossils within. So by understanding the layering of the Earth, we can understand change over time in the Earth, and the fossils then tell us about changes in life. Stratigraphy does have quite a long history, but one of the earliest founders of stratigraphy, who's sometimes called the grandfather of modern stratigraphy, is Nikolai Steno from the 1600s. Steno first proposed these ideas that we would now look at as like logic problems and common sense, but they hadn't really been enunciated yet, so he's given some credit for that. The three big important stratigraphic principles that Steno proposed are superposition, original horizontality, and lateral continuity. Now, if you've had a previous geology course, you may have covered these before. We're going to spend some time reviewing them now. Superposition is simply the concept that if you have a layer of sedimentary rocks, the relatively oldest rock is going to be on the bottom, and the relatively youngest rock is going to be towards the top. This is in an undisturbed sequence, and I point out that undisturbed sequence caveat because sometimes you can have entire sequences of rocks that can be folded and overturned, and that can mess up your superposition. But you can usually tell when that's happened. So in an undisturbed sequence, the youngest will be on the top, the oldest will be on the bottom, and we have a kind of a cartoon there on the right demonstrating that during time 1 we deposit rock 1. During time 2, rock 2 is deposited on top of rock 1, and so on and so forth until we get to time 5. 5 would be the relatively most recent. 1 would be the relatively oldest. Now, how old are these in absolute terms? How many millions of years or thousands of years? We don't know. And regardless of what those numbers are, this is still an accurate reading, right? This is still an accurate way of looking at things. So I guess one way of looking at this is I could, hypothetically look up YouTube statistics and figure out at what time did the first student in this class this semester log on to watch this video, and when was the last student to finally log on and watch this video. That would give me absolute times. Regardless of what those times are, there is still a first person who's going to see it, a second person, a third person, and a last person, and so on. So when we talk about relative age versus absolute age, relative age doesn't deal with numbers. It's things like superposition. It's just a sequence of events. And in this case, the sequence is that the oldest layer is on the bottom and the youngest layer is on the top. Our next stratigraphic principle, original horizontality, takes something like superposition to the next logical step. This is the observation that sediments are originally deposited in nearly horizontal layers. This is important because as we look around the world at sequences of stacked sedimentary rocks, or strata, we notice that strata can come in a wide variety of forms. It can be undeformed, like we see in Figure A. This is really the way things are normally deposited. In Figure B, we see tilted strata. This is a sequence of rocks that have been uplifted and tilted like a ramp. In Figure C, we have strata that pre-exists and then it is squeezed like an accordion, giving it this folded appearance. And then in D, faulted strata, where they used to be continuous, but now they've been fractured and our strata have been displaced. Notice where sequences 1, 2, 3, and 4 are offset on one side of Figure D than the other. Okay, so Figures B, C, and D all have to happen after the deposition of sediment initially, like we see it in Figure A. So if you go look in lakes today or rivers today, sediments are deposited in more or less nearly horizontal layers. So if they've been tilted, folded, or faulted, that had to happen after they were deposited. Rocks don't deposit folded. They don't deposit faulted, and they don't deposit really high angle tilts. So essentially this is saying, when we talk about an undisturbed sequence for superposition, these are some of the disturbances that a sequence can exhibit. How do we know what the original sequence is if it's been disturbed? How do we know what is the original up and the original down? We use things called primary sedimentary structures. These could be things like footprints or raindrop impressions on a mud flat, or mud cracks from rocks and sediment drying up and producing cracks. These are all things that are going to happen at the surface. So if you find them at the bottom, it means that there's been some kind of disturbance. But the main takeaway of this is that sediments are deposited horizontally in nice flat strata like you see in Figure A. What happens in B, C, and D has to happen after. So in other words, you can't fold rocks that don't exist yet. We have to have them deposited first, and then we can modify them to some degree. So let's look at an example. So here we have an image of an outcrop. You can see we have a couple of different colored rock layers. We have some sandstones, some siltstones, some shales, green, red, and some kind of cream color. And they don't continue all the way across the screen. They've been bisected by cracks. So let's start by first labeling our sequence of events. That green unit at the bottom is number 1. That is the oldest deposit. And then 2, 3, 4, and 5. Okay, so 5 is relatively youngest, 1 is relatively oldest. So here are our distinct sequences. Notice the pattern in the coloration where we have that greenish rock at the bottom, and then we have a band of white, and then reddish with a little bit of green on top, and then another white, and then another red. And we can see that we have the same sequences on both sides of this central area, but they have been faulted. They've been disturbed. So this is a situation where the order of events is we had the deposition of rock 1, the deposition of rock 2, rock 3, rock 4, and then rock 5. And after rock 5, we faulted this area. Now, from this image, it's hard to tell which fault happened first. We can't determine that. But the faulting happened after rock type 5 was deposited. We know that because rock type 5 itself has been faulted or fractured. You can't fault or fracture a rock until it exists. So we have sequence 1, 2, 3, 4, 5, and then faulting. The last of our Steno principles is original lateral continuity. And this kind of piggybacks off of the previous slide where we had our outcrop of our 5 different rock types. Remember, they had been fractured, so they weren't continuous across the screen. They used to be before there was faulting, before there was disruption. So we have original horizontality, that rocks originally deposited in nearly horizontal beds, as we can see with this sandstone layer here. There's some exaggeration going on in the far left. But notice how our sandstone layer in Figure A doesn't just stop. it gently pinches out as we get further to the right. It gets thinner and thinner until eventually it's gone. That just means the sediment didn't get past that point when it was being deposited. But if we look at figure B, we're missing two different areas of that sand and siltstone. Now this is due to erosion, probably a couple river channels carving through this area. It removed some of that sediment after the fact. Original lateral continuity states that the original deposited strata extend continuously in all directions to the basin edge. They don't just abruptly stop. So what we can do is kind of fill in the dots here, or we can connect our units. This is how they used to connect, right? But we've removed that due to erosion. Okay. So superposition, original horizontality, and original lateral continuity. So for example, if you ever go to the Grand Canyon, which is a breathtaking place, and you see all of these strata, these ancient depositional environments preserved in the rock, you'll notice that towards the top rim of the canyon you have this white sandstone unit. That extends throughout the entire canyon region and beyond. However, it's missing in the actual middle of the canyon itself, because everything's missing in the middle of the canyon because it's been eroded away. However, this white sandstone unit that's present throughout the region used to be continuous until it was eroded away. Now, since we are on the topic of erosion and how we can interpret strata, we need to mention this phenomenon known as unconformities. Unconformities, it's a little bit of an abstract concept because this is the part of the geological record that is not represented by, well, anything. Unconformities are surfaces between two rock types that represent significant amounts of geologic time. These are time periods when we don't have any deposition going on, or we have the erosion of previously deposited sediments. Essentially, it's a hiatus. So imagine that a lake with water flowing into it and sediment coming along with that water. And it's like a machine just dumping sediment slowly into this pond or lake over and over and over again for years. And then let's say we have a change in relative sea level and we stop depositing anything into that lake for a few million years. And then we turn on the sediment supply again and we start dumping sediment in. There's going to be a surface in between that initial deposit and our second deposit. And that surface represents the time where we weren't depositing anything. It's a hiatus. It's a break in the geologic record where we either stopped depositing things or we eroded things. So diastems is a term we use for a relatively short hiatus in a otherwise conformable sequence. This could be like a seasonal break in deposition or a seasonal influx in deposition. A bedding plane is essentially a diastem. So each layer of sediment that you see in a sedimentary rock is essentially a little package of time that's represented by sediments. And in between those, we have those surfaces that they cleave apart on that represent the absence of geological activity. So we have a few different types of unconformities. The first of them is a nonconformity. This is a situation where you have exposed metamorphic or igneous rocks. They've been eroded and you start depositing sedimentary units on top. So in this case, the unconformity is here. It's the boundary between our granite and our sandstone. Granite being an igneous rock, and notice I have chunks of the granite in the sandstone as well. That tells me that that granite was exposed at the surface, was producing erosional products, rubble and gravel, and those got incorporated into the later sedimentary rocks in between. So the time that's represented by the unconformity here, not the granite, not the sandstone, but the actual where I drew the red line, that unconformity, that represents the time in between the granite forming in the earth and when the sandstone started depositing. So think of this almost like reconstructing the order of events from a geologic perspective. So here's an example of a nonconformity. So here is the boundary right here. Notice that we've got this kind of pinkish rock underneath. That is the Pikes Peak granite that formed hundreds of millions, maybe billions of years ago. And then above it we have the saltwater sandstone, which is considerably younger. So we have that red line represents the time in between. Another kind of unconformity is an angular unconformity. In this case, we've already kind of talked about this a little bit, but we have horizontally deposited sediment. Those sequences are uplifted and eroded off the top, and then we have horizontal deposit happening afterwards. So in this case, our angular unconformity is where our rocks at the top are horizontal and our rocks below are not. Okay? That unconformity represents the time in between the original deposition and when it started to tilt and when we started depositing horizontal units again on top. So here's an example of an angular unconformity. Notice that our units on top are more or less horizontal and underneath they are not. These are very large structures. I want to point out the person that is waving down here. So yeah, these are very, very big features. So the underlying folded rocks were once flat. They were squeezed and folded and eroded off the top, and then we started depositing sandstone on top of that. The unconformity, our red line, represents the time in between the initial tilting and the initial deposit of the sandstone above it. Again, this is a geological concept that is not represented by rocks. In fact, it's the absence of rocks. Finally, we have our disconformities. Now, these are probably the most common types of unconformities we see, and they're actually the most difficult to identify. Because in some cases, you get this nice twisty erosional surface. In other cases, it's just a flat surface and line. But in this case, we have deposition of sediment. It's not uplifted. It's not tilted. It's sedimentary rock. We then stop depositing for a period of time, and we increase the rate of erosion. And then we start it all over again. This is actually what we have here in Oshkosh. If you go outside and you strip away all the dirt in your backyard, you are going to see probably 10 to 12,000 year old glacial deposits underneath the sediment, underneath the soil, the dirt. Beneath that, you have 400 million year old limestone. So we have 400 million year old limestone capped off with 10,000 year old glacial sediments. That's a lot of time in between that's simply represented by a surface. So that would be a type of disconformity. And these can be very difficult to identify. There's a disconformity here, and it's right along this gap right there. The Trenton and Black River formations are both carbonates, both types of limestones, and we just had the Trenton deposit, then it stopped, and then the Black River took over. If you didn't understand unconformities, you might think this is all one unit. There is another way of telling if you have a disconformity, though. That's a common question I get. How do I know if there's a disconformity there? Because the fossils that you find in the lower portion are likely very different than the fossils you find in the upper portion. And that suggests we have a significant amount of time in between. Now let's put all of this together into a concept known as cross-cutting relationships. This usually deals with some kind of igneous intrusion, like magma burning its way up through rocks that already exist, magma coming up from deeper in the earth, or possibly a fault that is breaking rocks throughout a region. So how do we figure out the order of events? Well, we want to apply superposition, original horizontality, and lateral continuity, and our concept of cross-cutting relationships. That any type of cross-cutting relationship, whether it's an intrusion or a fault, has to be younger than the material it is intruding through or cutting through. Again, you can't intrude or cut a rock that doesn't exist yet. So while we might want to be tempted to say that this diagram applying superposition, that the oldest rock would be I because it's on the bottom. I is an igneous intrusion. It is actually intruding through rocks that already existed. So really, our oldest rock here would be J. After J was deposited, we had K, and then F, and then H. And before we go any further, notice that the sequence KJFH is tilted. Well, we know from original horizontality that rocks aren't deposited like that. They're deposited horizontally. Sedimentary beds are horizontal. So we had JKFH, and then the next event was uplift and erosion. After that, we have the deposition of B. So notice that the unconformity we have between B and H is an angular unconformity. So we have rock type B is deposited, and then we have rock type G. And we know that G is after B because it cuts through B, but it doesn't cut through E, which means that it had to be between B and E. So then we have rock type E depositing after G is eroded away a bit. And then notice over here with D that we have faulted E and B. So D has to come next. Then we have I, our big igneous intrusion that burns its way up through the crust. And we have a little bit of that exposed on top of E when that in and of itself is buried under C, and C then is capped with A. So looking at it from oldest to youngest, we have J, K, F, H, then tilting and erosion, then B, then G, then E, followed by D, then I, C, and A. What I'd like to do now is talk a little bit more about some of the other founders of historical geology. We kind of covered everything that Steno was proposing, but I'd like to look at some other individuals too and their contributions. First, here is Johann Lehmann. Lehmann proposed that the rocks in the earth, especially in the crust, can be subdivided into three categories based on their general properties or lithology. These would be what he called ore, the stratified rocks, and the alluvial mountains. Now, we don't really use these terms anymore in this context, but what he was alluding to is what we would later call the three main rock types we have: sedimentary rocks, metamorphic rocks, and igneous rocks. Today, we still use the word ore, but it usually describes a rock that has some kind of economic value. So a lot of our igneous and metamorphic rocks do have some kind of metals in them that can be smelted out. So in this case, he was kind of mixing what we would later call sedimentary and, metamorphic and igneous rocks. But it's a term that we still use today in a different context. What he was referring to as stratified rocks would be sedimentary rocks. These are rocks that are formed in strata or layers. And then what he was referring to as alluvial mountains, today we would kind of see these are remnants of predominantly metamorphic rocks that would have been formed during mountain building events when they'd be squeezed and heated and uplifted. So while we don't use these terms anymore, the evolution that got us to igneous, metamorphic, and sedimentary started with Lehmann and his ore, stratified, and alluvial mountains. So again, here's a situation where he wasn't exactly accurate, but it was the first stage at a better understanding of the rock cycle. Another geologist we should give a little bit of attention to is the father of Italian geology, Giovanni Arduino. Arduino was one of the first geologists to propose that not all rocks were deposited at the same time, and that you can actually look at some of the properties and fossil content of rocks and get an idea of roughly what age they are. Now, he used four age criteria, what he called primary, secondary, tertiary, and quaternary. And though these aren't terms we use exactly the same way anymore today, it did usher in what we now use as the basis of our geologic timescale. Another impressive aspect of Arduino, and really many of these old geologists, is that they didn't have cameras, so they had to actually sketch the rocks that they see. So this is an image actually from Arduino's sketchbook, of his field notebook, and then translated below are kind of the terms that he used in his descriptions for them. So what he was calling primary or primitive rocks, he described them as rocks that fell to the bottom of a pile and had metallic ores but no fossils. He was kind of thinking of these as the oldest rocks that are available. And in some cases he's right, and in some cases not. Not having fossils doesn't necessarily mean that it's old. It could be an igneous rock, for example. But his secondary rocks, he said, included marbles and limestones, often tilted, contained fossils, but compared to what lives today, they looked very strange. And that's because he's looking at mountains in Italy where these rocks have been uplifted and deformed. So limestones transformed into marbles through metamorphism. But in those limestones, and sometimes even in the marbles, you can see fossils from the Paleozoic era. So what he was calling secondary would really be more Paleozoic fossils. What he was referring to tertiary, rocks that sat on top of the secondary layers, so through superposition would be relatively younger, but contain fossils that are much more recognizable, quote, very perfect and wholly similar to those that are seen in the modern sea. We would actually refer to these as Mesozoic rocks because that's when we start seeing more of our marine faunas, similar to today, having their origins. And what he referred to as quaternary were the sands and gravels resting on top of tertiary rocks. These would be glacial deposits that are relatively more recent. So it's not an exact perfect model for what we use today, but this is the founding kind of starting point for our modern day geological timescale. A very important contributor is Georges Cuvier, who in the early 1800s conceptualized the concept of extinctions. Now I want you to think about that for a moment. Before Cuvier, nobody had really given thought to the idea that organisms can go extinct. Before this, everybody thought that every animal that ever has been alive is still alive. Cuvier was the first one to notice that we have things in the fossil record that are very, very different than anything we see alive today. These are organisms that must have gone extinct. And this was a pretty revolutionary idea. Now, that being said, Cuvier had a very kind of limited scope as far as what caused extinctions. He found his view was that all extinctions were caused by biblical catastrophes. So he's the founder of what we would call catastrophism. That all extinctions are explained by big floods that wipe out all life, just like in the Judeo-Christian Bible, and then you'd get new life forming after that. We now know that those types of, we do have catastrophic events like asteroid impacts, volcanic eruptions that can cause extinctions or put major stress on ecosystems. But we also have organisms that just go extinct because they are outcompeted by another organism in the ecosystem. So we don't actually subscribe to catastrophism anymore, but we kind of want to make note of where the concept of extinction is founded. He also co-developed what we call the principle of fossil succession, which is a very important tool that we still use today to get a relative age of rocks based on fossils. Fossil succession is a very important concept for understanding the order of events and being able to tell relative time with fossils. And this is based on two criteria. First, that fossils have a first and a last appearance. So if you're looking through rocks and all of a sudden you find a new fossil, that first appears in the geologic record somewhere. And then it's somewhere else in the geologic record, it doesn't appear anymore. And these roughly coincide with speciation, the evolution of a new species, and that species extinction later on. So for example, we have our paleontologist down here who's working in some rocks. They're sitting on unit 1 and they're working inside of unit 2. Notice that the fossil we have in unit 1 is A. And fossil A, we don't know when it starts because all we're seeing is this lowest unit, but it persists up until the boundary of 2 and 3, and then it goes extinct. So that means just based on what we're looking at, fossil A is present in unit 1 and in unit 2. However, in unit 2, we also have fossil B, which starts at the boundary between 1 and 2, and it persists and goes extinct between 3 and 4. So we have a significant overlap. Rock unit 2 is the only place where we have fossil A and B present at the same place and at the same time. Notice then unit 3 has fossil B and fossil C at the same time, but unit 4 just has fossil C. And we continue from there. So we have every fossil has its own first and last appearance and its range, and some of these ranges overlap, and that allows us to tell time. And we can also correlate these rocks with rocks locally, regionally, or even globally that have the same fossils, because since fossils have a very distinct duration of time in which that organism existed, maybe only a few million years, we can overlap and look at the overlapping ranges to help us constrain time. So this was one of the concepts that Cuvier helped develop as he was coming up with the concept of extinction. And again, extinction is half of the story of fossil succession. The other co-developer of fossil succession was Mr. William Smith, who was a geologist and actually a cartographer from England in the early 1800s. Smith was obsessed with developing stratigraphic concepts and techniques. In fact, there's a great book about him called The Map That Changed the World. Smith actually made the first geologic map of England by hand. He traveled the entire countryside and he took geologic samples and he identified fossils. And by the way, that image of the fossils there is one of William Smith's watercolors. There weren't cameras, so he drew everything, and his sketches are still considered to be some of the best. Smith had a very interesting experience, though, because once he collected all of his data, which took decades to do, he went back home to London and found that his wife had left him and that he was locked out of his house because nobody had been paying the bills. So he had to go to debtor's prison for years. And while he was in debtor's prison paying off his debts, the British Geological Survey stole the credit for his map. And it wasn't until many, many, many years later after his release that he was able to get the proper credit where it's due. So it's a fascinating story. Again, the book is Map That Changed the World. I highly recommend it. William Smith is a really fascinating historical character in geology. James Hutton is another important contributor to historical geology and paleontology. He's considered to be the father of modern historical geology, and he developed the concept of uniformitarianism. Now, this is an incredibly important concept, and I'm going to go through the basic, the long-winded definition, and then kind of the bumper sticker meme version. So the past history of our globe must be explained by what can be seen and to be happening now. In other words, the present is the key to the past. Not the past is the key to the present. The present is the key to the past. So if you want to know how an ancient sand dune was formed back in the Jurassic period, you should probably go look at modern day sand dunes and watch how they form. The present process is the key to understanding the past process. Boy, does this seem like common sense, right? Well, it took a while to get here. And we have to be careful with uniformitarianism. And that's because while it's certainly true that if you want to understand ancient environments and processes, look at the modern equivalent happening today, sometimes all you have is the modern equivalent, not the actual same process. For example, today we plant a lot of grass around yards and in between highways and so on because grass is really good at gripping soil and it reduces the rate of erosion. So anywhere grasses grow, you have a reduction in the rate of erosion. Grass didn't evolve until the Cretaceous period. So if we could go back in time to the Jurassic period, there was no grass. So were erosion rates higher? Probably, or very likely. These are some of the things we have to think about. This doesn't necessarily say that all life is the same. It says that geological and natural processes are the same. Life, grass being one kind, not being around means that we're not going to have the same kind of erosion rates, but the physics is still there. Really what uniformitarianism is saying is that the laws of physics and chemistry are uniform throughout time. So what your understanding of a process today is physics and chemistry at work. And those don't change just because a couple of years pass. Charles Lyell was another contributor to the concept of uniformitarianism, and he really rebelled against the concepts of catastrophism that Cuvier was proposing. Because what Lyell understood was that most, not all, but most geological processes are very, very slow. Thus, they can't be explained by simply all catastrophes. Geological phenomenon can be catastrophic, but Lyell didn't really give too much credence to that. He just said, hey, erosion is slow. It's slow today. It must have been slow millions of years ago, which means the Earth has to be millions or billions of years ago. He was one of the first people to really push for an old Earth view, though we didn't have a full understanding of how many years yet at that time. Okay. So uniformitarianism had this very kind of, ironically to say, this kind of a fire and brimstone approach where it was like, if nothing happens quickly today, then nothing happened quickly in the past. All geological processes are slow. We now know that that's not entirely true, though. The modern view of uniformitarianism states essentially, like I said, that the physical and chemical laws are uniform and operate in the past just as they do today. However, the rates of these laws and the types of processes have changed. So there are catastrophic events, hurricanes, earthquakes, volcanic eruptions. These can drastically change a landscape in a terrestrial setting very, very quickly. And it's something that the old view of uniformitarianism didn't take into consideration. We just know today that these types of catastrophes are not as common or as persistent as boring, slow geological processes. We also accommodate short-term catastrophic extraterrestrial events. No, I don't mean aliens. I mean meteorite and cometary collisions. Lyell didn't accept those. He didn't understand any evidence for those. We now know, yeah, asteroids hit planets, sometimes ours, and it can very, very quickly change the Earth, change a lot about it. So we've defined and refined the definition of uniformitarianism. We can still summarize it as the present is the key to the past. Just understand that there's a little more to it than that. Another geologic principle I want to bring up is the concept of inclusions. And we've seen some evidence of this already in our discussion. But if you have rocks that are exposed at the surface and they start eroding and producing pebbles and boulders and cobbles, and then those get incorporated into a later sedimentary deposit, those eroded products, those inclusions, are older than the material surrounding them, as we see on the example on the right. The example on the left, though, this thing called a xenolith, that's a little bit different. That's where you have rocks that pre-exist, and lava or shallow magma can burn its way horizontally through those rocks, causing some of the overlying rocks to fall into that body and become entrapped. Those are still older than the rocks surrounding them. So any kind of fragment or inclusion is going to be older than the rock mass that is encompassing them. In order to include something, it has to exist first. Let's take a moment and do a little self-quiz. Obviously, this isn't something that's going to be graded. It's just a kind of a quiz to help you gauge whether you're really grasping the information that we've covered so far. So, our first question is, who first proposed the concepts of superposition, original horizontality, and lateral continuity? One person proposed all three of those. Number 2, briefly describe the law of superposition. Number 3, briefly describe uniformitarianism. Number 4, name one of the two individuals who founded the concept of fossil succession. And finally, which unconformity represents the time that occurred in between the erosion of non-sedimentary rock, such as igneous or metamorphic rock, and the deposition of sedimentary beds above it? So something like this. What type of unconformity would that be? So now let's go over some answers. So who first proposed the concepts of superposition, original horizontality, and lateral continuity? That'd be Nikolai Steno. On an exam, I wouldn't be asking anything about specific dates, just like a last name and know their contribution. So, briefly describe the law of superposition that Steno proposed. It can be best summed up as, in an undisturbed sequence, the oldest is on the bottom, and it gets progressively younger as you move up section. What about the law of uniformitarianism? That would be best summarized as the present is the key to the past. Now, if you said the past is the key to the present, that is not accurate. We don't look at the past to understand what's going on today. We look at environments today to understand how the past may have worked. Name one of the two individuals who founded the concept of fossil succession. Well, you could have said either Smith or Cuvier. Both of them utilized and developed that concept. And finally, which unconformity represents the time that occurred in between the erosion of non-sedimentary rock, such as igneous or metamorphics, and the deposition of sedimentary beds above it? This would be a non-conformity. Remember, an angular unconformity would be if the rocks are folded or tilted, and a disconformity would be sedimentary rocks with a break and then on top of more sedimentary rocks. So in this case, it'd be a nonconformity. Now, if you didn't understand any of these questions or you didn't get any of them right, I would recommend start looking over your notes regularly. Watch the videos maybe more than once, review your notes, take some extra notes, and feel free to please ask any questions that you might have. You want to make sure you have this information under your belt before we get into the first exam. Let's change gears a little bit and look at fossils, fossilization, and the importance of fossils in the geologic record. So what exactly is a fossil? Well, believe it or not, this is a word that's commonly used in geology and obviously paleontology, but is not easily defined. It's based on the Latin word fossilium, which loosely means to be dug from the ground. So in its earliest usage, anything that you pulled from soil could be considered a fossil, even if it's just a rock. Since the 18th century, though, it usually referred to some kind of ancient shell or bone. Today, though, we recognize fossils as being as a more diverse term than just representing shells and bones. There's a lot of different things that we can describe as a fossil, and I want to go into some of the differences here for a few minutes. The modern definition of fossil more or less means any evidence of past life, so not necessarily just a bone or a shell. And this is what I mean. I want to kind of get into what this definition of any evidence of past life really means. While a shell or a bone are certainly types of fossils, if they're very old and from some form of ancient life, really we expand the definition of fossil to really include any evidence of past life. But to separate it from archaeology and human behavior, we add this caveat that any evidence, preserved evidence, or trace of past life that is naturally protected from rapid degradation. So in other words, if we take a dead plant or animal and we bury it and put a tomb over it, that's not naturally protecting it from rapid degradation. That's a human behavior being used in something in nature. So any preserved trace of past life, that could be parts of an organism, such as bones and shells and teeth and claws. It could also be a footprint, which is not part of the body, but it is a preserved trace of past life. So those are our big criteria. It has to give evidence of life and be naturally preserved. So it either has been or has the potential to be naturally preserved within a geological context. So this way we can kind of separate out the anthropological aspects and focus more on organisms that may have existed in the past and how we know they existed in the past. Maybe it's from finding shells and bones, maybe it's from finding footprints, maybe it's from finding fossil fuels. So this definition is kind of evolving, but one thing that I want to make very clear is the absolute age is not important, and it's unfortunate. I've actually been in museums where they have signs up saying, in order for something to be a fossil, it has to be this many millions of years old, and that's not true. Something as young as just a few centuries old can be considered a fossil. It's any evidence of past life that has the potential to be protected from rapid degradation, naturally. So however old it is, doesn't really matter. There's a couple of things, though, that's really important to remember about fossils. When you look at a fossil shell, let's say like a fossil clamshell, you're not looking at the entire animal. You are looking at a subset of that original animal. Specifically, you're looking at the mineralized parts, like a shell or bones. But if you think about even ourselves as living beings, we are not simply a skeleton with stuff on top of it. What makes us living is soft tissue. It's our brains, it's our organs, it's our skin, and everything like that. Our skeleton is an important part of our bodies, but it's not the foundation, right? Mineralized parts like shells and bones grow in response to soft tissues. So when you were developing before you were born, you had a brain before you had a skull, okay? But the hard parts in organisms are what have a better chance of preserving. So what we're looking at when we look at fossils is a subset of the original plant or animal. And we have to figure out ways of inferring, not guessing, but inferring what those living biological tissues would have done and what they would have looked like and how they would have worked. So as we mentioned, to preserve a fossil, it helps if we already have some mineralized hard parts. Those are going to make very good fossils in most cases. Again, not to say soft tissues can't fossilize, it's just rare. So the organic components break down quickly. And this is where I want to really stress an important thing again, and that's that when you look at all the shells on the screen of these little gastropods and bivalves, these invertebrate organisms, the actual animal that produced those shells is gone. All you're looking at is the exoskeleton that's left behind. Okay, so the part of the organism that actually made it living is gone. Those organic components degrade very, very rapidly, leaving behind essentially these little mineralized structures that were grown by the organism, and now they can behave like sediments when we form sedimentary rocks. They can be tumbled around, they can be broken, they can be accumulated. So to preserve a fossil, it's good to have readily preservable hard parts, mineralized tissues like shells or bones. So what are these hard parts made of? Well, when we're dealing with invertebrate organisms like corals, like clams or oysters, or even snail shells and so on, they're usually made of something called calcium carbonate. That's that CaCO3. And this can be in the form of calcite, though technically, if it's a true mineral, it wasn't grown by an organism, but we'd say a carbonate shell in the form of a calcite or aragonite-like chemical structure. Aragonite is a biogenic form of calcite or of carbonate that will degrade to calcite. So we have carbonate shells that behave like calcite. And then we have calcium phosphate, which is typical of vertebrates. This is what our internal skeletons and teeth are made of. It's actually, if it were a mineral, it would be called apatite. But bones and teeth and claws are made of calcium phosphate, which is also a really strong, durable material. Occasionally, though it's quite rare, we do find some small fossils that have been opalized. They can preserve as opal, which is a hydrous silica. And then complex organic compounds. So pollen would be an example of this. Or more recently discovered collagen in dinosaur bones can actually preserve for tens of millions of years. So when we're looking at preservable hard parts, these are things that undergo a little bit of alteration or no alteration at all. For example, I've collected dinosaur bones from Montana that haven't been permineralized very much. They weigh about as much as the original bone would have weighed back in the Cretaceous period. And then you have others that have been fully permineralized, like in the Morrison Formation, the Upper Jurassic rocks of like Utah and Wyoming. So different types of taphonomic histories, different types of settings, all of those things we just talked about for filters play into how even our hard part fossils are preserved. Now, when you hear the word fossil, an image might pop into your head. Maybe it's a dinosaur bone, maybe it's a fossil shell, maybe it's a fossil trilobite or a fossil leaf or something like that. But there's different types of fossils, and I want to talk a little bit about the different kinds because each one tells us something a little different. The first kind is a body fossil. Body fossils represent actually part of the organism. So for example, this is a cast or a replica of the body fossil of a small pterosaur. This is a pterodactylus. Okay, so when you have bones or shells or teeth, that's a representation of the organism's body, and it tells you something about anatomy. You might be able to tease out a little bit more information concerning physiology, but mostly it's telling you something about how that organism looked. The next type of fossil is known as an ichnofossil or a trace fossil. We use those words kind of interchangeably. This isn't usually going to show you a bone or a tooth or a shell. It's going to tell you more about how that organism lived. So this is any kind of trace that's in a rock, or maybe it's in another kind of fossil, that tells you about how an organism was behaving. So for example, this is another cast, and if I hold it up, you can just see this structure here and up here. These are the footprints of a pterosaur. So this isn't the body of a pterosaur, but it is a representation that this organism was alive and that it was walking. So this tells us more about how pterosaurs walked. So this would be a trace fossil. This also includes things like other types of footprints. It can include bite marks, eggs, or coprolites, which is fossilized poop. All of these tell you something about how that organism was living and interacting with its environment and other kinds of organisms. So body fossils tell us anatomy. Trace fossils tell us something about behavior. And it is possible to have both in one. So for example, if you have a dinosaur bone from a big plant-eating dinosaur and you have bite marks from a carnivore, the body fossil is of the plant eater. The bite marks are telling you the behavior of the carnivore. So you're getting a trace fossil from one on the body fossil of another. It doesn't happen a lot, but it's really cool when it does. And finally, we have what we call chemofossils. This can be a representation of the organism's anatomy, but not always. It's any kind of chemical signature preserved in rock that indicates presence. So in this little piece of shale, you can see a fossil leaf. Okay, but all that's left is a carbonized film of that leaf. The actual leaf itself is gone, but what it's been reduced down to is just pure carbon, which is the basis of these types of cellular organisms, right? Carbon-based life forms. So chemofossils include fossil fuels. So natural gas and petroleum are the broken down remains of fossilized organisms, or from millions of years ago, microscopic marine organisms. And those count as a chemofossil. So let's talk a little bit about modes of preservation, specifically for our body fossils. Okay, the first one we're going to talk about is called permineralization. In this case, you start out with something that is porous, like bone or like wood, and after it's buried, groundwater that's flowing through the sediment that's buried these materials precipitates out very small amounts of dissolved minerals that will grow into those open pore spaces. I guess one way I like to describe this is if you took a dish sponge and you soaked it entirely in something like super glue, it wouldn't have the same properties of a sponge anymore because all those open pore spaces would be encased with glue. And that's the same kind of process that's happening here with bone or with wood. So those open cavities inside of wood that are used to conduct water through those tissues, or the marrow cavities or openings for blood vessels, the lacunae and things for nerves and so on, in bone can absorb these waters as they're flowing through the ground, and you can start almost like a geode, those little cavities fill in with dissolved minerals. So for example, this is a slab of dinosaur bone that's been cut and polished with a rock saw. And if you look at it up close, you can see all those tiny little pores, those little openings that would have been for the spongy bone, the spongy end of the bone of this limb, so some of that marrow cavity, but now it's been completely filled in with silica. The original bone is still there. It's still calcium phosphate. It's still apatite, but it's now been permineralized with silica, with essentially microcrystalline quartz. So it's increased its density and its hardness, and it weighs a whole lot more. Now, the next couple of modes of preservation we're going to talk about predominantly apply to invertebrate fossils, so things more like shells of things you'd find at the beach. Most of these shells are produced out of calcium carbonate, a biogenic or biologically grown form of calcite. It's CaCO3, so it's calcium carbonate, the same stuff that the mineral calcite is made of. One type of preservation of a shell is called recrystallization. In this case, our original calcium carbonate shell is buried, but over time, that shell will start to dissolve. As water moves through the sediment, it will slowly start to break down that calcium carbonate. Think about the same way if you had a glass of water and you added salt to it and stirred it up. The salt crystals would dissolve. But just like in that same example, if you were to boil the water off, those salt crystals would grow back. And that's kind of what happens with recrystallization in shells. The original calcium carbonate shell is buried. It undergoes dissolution, and so you have a fluid left in that cavity of dissolved calcite in water. And then due to low-grade metamorphism, where we apply a little bit of heat to that rock and pressure, the calcite starts growing these nice big euhedral crystals. So if you look at some of the spots here, like this portion of the shell or this portion of the shell, our first one here, that is what's actually grown by the organism when it was alive. It took a little bit of calcium and a little bit of carbonate for ions out of seawater in its diet, and it grew this shell. But then the shell was buried and started to dissolve, and then our nice euhedral or nice prismatic calcite crystals started growing back. So this is a taphonomic modification. If you were to find this particular fossil shell in a quarry when you were collecting fossils, you'd know that, okay, the animal didn't grow these nice big crystals. They grew the tiny microscopic ones, and this would be an example of one of the changes that happens during fossilization. Our next mode of preservation is very similar to what we just talked about with recrystallization, and actually follows a lot of the same steps leading up to actual diagenesis or alteration. In the form of replacement, we go through the same steps. We start with a calcium carbonate shell, we bury it, groundwater dissolves away the original calcium carbonate, but in this case, instead of regrowing that calcium carbonate is removed, and something else grows in its place, usually something a little different that normally an organism wouldn't naturally grow. In this case, you're seeing on the screen is pyrite. So we had an original calcium carbonate shell, we dissolved it, and then due to low-grade metamorphism, we actually grew pyrite, or also known as fool's gold, and as you can see on the right is the original mineral form of that in its place. So this can happen quite a lot with pyrite. It can also form with silica. You can have a calcium carbonate shell that is replaced with silica. It can also happen with things like precious gemstones as well. So we can have a lot of different types of replacement, though replacement overall is pretty rare. Now, possibly the most common types of invertebrate fossils you would find have these types of modes of preservation: molds and casts. So in this case, we start with this very familiar setup. We take a calcium carbonate shell, we bury it in sediment. Groundwater moves through the sediment and slowly dissolves away the shell. But instead of replacing it or recrystallizing it, it's just gone. So you're left with a hollow cavity. Now, this hollow cavity is usually going to be the external surface. So in the image on the lower left, you can see we have a snail shell, but actually the shell isn't really there. Within that, you can see the impression of the shell, and then next to it is what we call a cast. That's if that mold or impression were to be filled in with something else, like sediment. So we start with a shell, we bury it, we dissolve it, and what's left is an imprint of what the outside of that shell looked like. If sediment were to be poured into that mold, what we call an external mold, we would produce a cast. But remember that some of these organism shells, such as snail shells, for example, or even clam shells for that matter, are hollow. Well, what would happen if sediment filled inside of that shell before the shell dissolved? That's what you see on the lower right. That's what we would call a steinkern, or an internal mold. It's not technically a cast because it hasn't been filled in from a mold. This is sediment that filled into the hollow cavity of the actual shell itself. So molds, casts, and steinkerns kind of follow the same general steps, but it depends on what kind of shell that we're looking at, which is going to tell us whether we get a steinkern or a mold-cast combination. So let's look at some examples of how molds, casts, and steinkerns form. So here I have the fossil of a trilobite. This is an invertebrate from the Paleozoic era, okay, a little marine bug-like organism. And I've got a piece of clay. So what I'm going to do is replicate what would happen if our trilobite fossil were buried in sediment. Okay, so I've compressed it into the clay. And now let's say our original shell is dissolved away. So we remove the fossil, and what do we have left but an imprint of what the outside of that trilobite looked like? This would be an external mold. Now, if I would take this and I would pour sediment into it or plaster into it, I would get a cast. It's a copy of the outside structure of this fossil. Okay, so this would be an external mold, and whatever I'd pour into that when it would harden would turn into a cast. Now, what about steinkerns though? So here I have two shells from a clam. Okay, now they're hollow, right? The inside of a clam shell is where the actual organism lives, and when it decays, it's just a hollow space. So what if before we buried this shell, we filled it with sediment? As you can see, I've done again with clay. And let's say we then remove our original shell material, it dissolves away. We're left with technically a mold of what the inside of that shell looked like. So a thing to remember about molds, molds are always going to be an inversion or an imprint or a negative of whatever the original material was. So if our original shell is hollow on the inside, our internal mold is a Steinkern. If we're looking at something that is convex on the outside and we press it into sediment and remove it, we're left with an external mold. So Steinkerns are not cast, they're internal molds, while these type of molds are external. So let's walk through our mold and cast process with an example. So here we have a happy little snail, right? You can see it's got a calcium carbonate mineralized shell, and then the rest of it is soft tissue. It's a living animal. It's a happy snail until it dies, and now it's not happy. So our actual part of the organism, the soft tissue, is going to decay away, and we're going to be left with a hollow coiled snail shell. Now, what can we do with this? Well, if we bury it, and that's all that happens, we have original preservation or unaltered fossilization, and everything's great. However, once it's been buried in sediment, it has a tendency to become altered in some way or another. So we start out with our unaltered shell, buried in sediment. Now, what happens if that shell dissolved away over time? Well, we would be left with an imprint of that shell and of the outside of it, and this would be our external mold, like we just showed with the trilobite and the block of clay. Now, if that mold were to be filled in with silt or another kind of sediment later on, we would have a cast. Now, the difference between a cast and the original fossil is if I took that original snail shell and I cut it in half, you'd see how it was hollow in the open cavities on the inside. If you cut this cast in half, it's just going to be solid all the way through. It's just been filled into a mold. So this would be a cast of the external features because it was made from an external mold. Well, if our snail shell would have been filled in with sediment prior to burial, and then we dissolved the shell away, notice we have this kind of open spiral on the inside of sediment, and that would be our Steinkern. And I want to step back for just 1 second because I mentioned unaltered remains, like if we took that shell and we buried it and that's where everything stopped. That does occasionally happen, even with things like vertebrate animals. In this case, the soft tissues can still be modified, but usually slightly. One way of doing this is to freeze something. So this, in the image in the background of the slide, is a frozen baby mammoth from about at least 12,000 years ago. This does happen, and in case the whole animal's there, it's just been frozen in ice. Desiccation, or drying out of plants, and also the formation of mummies, both natural and artificial, is a form of unaltered remains. It's still soft tissue, it's just all the moisture's been removed. And insects encased in amber, sealed up in amber, like the Jurassic Park mosquito idea. Yes, that does happen, except again, it's so dried out inside of that sap, inside of that amber, that if you were to crack it open, again, it'd be mostly just a carbon film, but the structures are still there. In all of these cases, this implies that there was a reduction or absence of microbial or chemical decay after the organism died. So in other words, there wasn't a lot of chemical breakdown of soft tissues. And one way to inhibit that is to reduce the presence of aerobic bacteria, things that cause rot. Bacteria that will break down cells. And a good way of doing that is drying things out, freezing them, or sealing them up completely. Let's talk a bit about our ichnofossils, also known as trace fossils. Remember, this can be any kind of footprint or track. It could be a trail. A pathology would be some kind of an injury or damage. It could be fossilized feces, a bite mark or feeding trace, anything that suggests the lifestyle or behavior of an organism. And it may not always tell us about what that organism looked like. Sometimes it does. The upper left image that you see there that's marked A, that's the left side of a juvenile T-Rex skull. And you'll notice right around the center of it, you have these three little slots that are present right about here. Those are bite marks to a tyrannosaur of pretty much the same size and age. Now, T-Rexes and most animals don't bite themselves on the face, so we interpret this as a bite mark from another juvenile T-Rex. So in this case, we have a body fossil with the trace fossils of something else. Happens to just be likely the same species. But I also want to point your attention here. So here we have an oyster shell, and right here, I'm going to highlight it in yellow, we have this little drill hole right through the back of this oyster shell. This is from a terrifying group of organisms that will climb onto the back of one of these bivalves. And it's usually when the soft tissue organism side, it's still alive. And this organism will crawl onto its back, and it has this really sharp beak and an acidic saliva, and they will secrete the saliva on that calcium carbonate shell, this acid, and which will cause it to react. And then they use their beak to grind a hole through that softened area until they puncture all the way through the shell and literally suck out the living organism inside through a tiny hole. It's really, really horrific to think about. By the way, the animal that's doing this, your typical variety of snail. Yeah, this is how predatory snails get their food. They drill holes through clams and then suck out the living organism. So it's gruesome, but really quite interesting. In either case, we have a body fossil of an oyster that tells us what the oyster looked like. The trace fossil tells us what the snail was doing, but together it tells us the relationship between these two organisms in their environment. We also have footprints, as you can see in the lower left. That is important. That's going to tell us whatever animal that was, whether it was walking on 2 legs or 4, in this case 2. In the upper middle, we have what looks like tire treads going through sand. Those are actually trilobite track marks, the little numerous legs of our trilobites as they scurried around. So we can learn how they moved and what types of patterns that they walked in. And then, of course, the thing that looks like poop, well, that's a coprolite. That's fossilized feces. Coprolites are really, really important. You can slice them up with a rock saw. They're lithified into rock, so it's not gross. And actually find things like fossilized seeds or bone fragments or bits of plant material to tell us what these animals were eating, what their diet was. Now, it's not always easy to link the coprolite to the organism that produced it, or in other words, it's not always easy to figure out who dung it. I know this is recorded, but I'm going to pause for laughter anyway. Or another way of thinking about it would be, who would be the poopatrator? I'll be here all week. Trace fossils also include things that we find at archaeological sites, such as spearheads and garbage, because even though it's not telling us what this particular civilization looked like, it does tell us about some of their habits, how they hunted, what they ate, what they discarded. This would also include any kind of borings or burrows through wood from things like termites or shipworms. And again, at the top of the screen, you can see more examples of these drilled bivalve shells, showing how common it is for gastropods or snails to actually leave their traces on the remains of other organisms. And finally, we get to our chemofossils. And chemofossils haven't traditionally been included in discussions on fossils, even though we use the term fossil fuel all the time. But really they are. Whether you're looking at natural gas or petroleum, any kind of hydrocarbon, or even coal, these are all derived from the remains of ancient organisms. It's a chemical leftover from an organism, but it also includes carbonization, such as that fossil fish. The bone and the scales there have pretty much all just been reduced down to carbon in this case. Some of the bone might still actually be calcium phosphate, but this also includes, and I have a DNA double helix there, even though that's not always the case, but it does include biomolecules. So things like collagen, possibly blood, and mitochondrial DNA. These are chemical traces of an organism, whether we still have that organism there or not. So these are becoming a more important aspect of paleontology, because now that we have a better idea of what kind of biomolecules we can get out of fossils, we can learn more about what we can do with those to tell us more about those organisms and the relationships to each other and their environments. Now, so far, we've talked about how mineralized hard parts can undergo alteration and soft tissue just breaks down or carbonizes. And while that is generally the case, there are exceptions, and one of those exceptions, or what we call those exceptions, are things called Lagerstätten. Lagerstätten is any type of fossilization situation where you have exquisitely preserved soft tissue. This allows us to get a better idea of how the physical living function of that organism worked. So we like to think of it as providing a window into the morphology and the diversity of life beyond what is normally preserved. So normally soft tissue breaks down and you're left with the hard parts. Lagerstätten would be having both in place. While carbonization is a type of chemofossil, it's also Lagerstätten. So in this case, we see some beautifully preserved leaves and some pine needles. And in the lower right, you can see a fossilized insect. These are all things that normally don't make good fossils because they're soft. A leaf will easily break down. And think about how easy it is to compost something. So the fact that we can get a leaf preserved well enough to look at the veination and the sawtooth ridges around that leaf is really quite exquisite. Insects generally, even though they are the most abundant form of life on the planet, don't make very good fossils, because if you see a bug and you step on it and it goes crunch, that means its exoskeleton's not very durable. And if that's the case, when they die, they tend to break apart and dissolve. So to have insects and leaves preserved is a form of Lagerstätten. This is Archaeopteryx lithographica. It is possibly one of the most famous fossils of all time. Archaeopteryx was a crow-sized vertebrate from the late Jurassic of what is now Bavaria. There's only a handful of Archaeopteryx specimens known, and they all come from the same locality in Bavaria, in a place called the Solnhofen limestone. So this organism died in a lagoon, and that's the type of very, very fine carbonate, calcium carbonate sediment that's surrounding it in a very thin shale. So it died in this lagoonal deposit and was buried pretty quickly. So what is Archaeopteryx? Well, if you look at the skeleton, it looks like a small meat-eating dinosaur, again, like a crow-sized dinosaur. It's got a mouthful of teeth, it's got fingers with claws, and it's got a long bony tail, and it even has a wishbone, which is a little strange because it's a dinosaur. However, when you look around the arms and around the tail, you can see these long impressions of feathers. This is not something that would normally preserve, so this is an example of Lagerstätten. So is this a bird or is it a dinosaur? And this is actually one of the most important specimens that teaches us that the relationship between meat-eating dinosaurs and birds is very, very close. And in fact, living birds today are a type of meat-eating dinosaur that didn't go extinct. So Archaeopteryx is really showing us that relationship. This is where bird versus dinosaur gets really, really gray. And we wouldn't know that as well if it weren't for the feather impressions on this example of a Lagerstätten. But our techniques and methods in analyzing Lagerstätten, especially on things like small vertebrates like dinosaurs, has really come a long way just in the last 2 decades. This is Sinosauropteryx prima from China. It's a very small cat-sized meat-eating dinosaur. And you'll notice on the fossil on the left, you can see a kind of a dark fuzz or filaments that are around the body. These have been looked at under scanning electron microscopes, and yeah, they're proto-feathers. It's what we call dino fuzz. It's similar to what you'd see on like the downy fluff on a baby chick or a duck. If we look very, very closely though at this dino fuzz, these proto-feathers, we find these little odd structures inside of those called melanosomes. Now, melanosomes are what give birds their feather colors. Just like with mammals, what gives us our color is a pigment called melanin. Different amounts of melanin change the tone of your skin. Similar with feathers, except melanosomes have different shapes. The little structures that give color have different shapes. So if you look at a black feather or a red feather under a scanning electron microscope, they're going to have different shaped melanosomes. So what these researchers did is they did a catalog of melanosome colors and the shapes that we see with modern birds. And then they looked at the dino fuzz on Sinosauropteryx and found that most of those melanosomes correspond in modern birds to orange-colored pigments. So the artist's illustration you see on the right of that cute little Sinosauropteryx with its orange and white stripes is actually supported by scientific evidence. That could be one of the more accurate depictions of an extinct organism. The same research team also went a little bit further and did the same thing with an organism known as Ancorus huxleyi, which is a Cretaceous bird from China. In this case, they had lots of feathers preserved and a nice complete skeleton, and they were able to say that, based on their analysis, that Ancorus had a red crest on its head. It was mostly black and gray with some white speckled feathers on its arms and legs. But what about something a little bit larger? This is Borealopelta. This is an ankylosaur, or one of the armored dinosaurs from the Cretaceous. This was found up in Canada. And in this case, we still have fossilized skin with pigments, some possible stomach contents, and the thing is preserved in 3 dimensions, so all of its armor plates are still intact. Now, we really only have about the front half for the most part of this animal, but the fact that it looks like it just kind of laid down the other day and passed away is really quite striking. So this would also be an example of Lagerstätten, because not only do we have the mineralized hard parts, but the way they're preserved and what's preserved with them tells us a lot about this animal. Let's talk about some of the major subdivisions of paleontology, because paleontology is, the study of ancient life, but there's a lot of different things that count as life. We have plants, we have animals, and there's different aspects of these research fields that people will focus on. So the 2 of the most common aspects of paleontology is paleobiology and studying concepts in evolution. So if you want to study fossil animals, you'd be doing paleozoology. If you're studying fossil plants, it'd be paleobotany. Some people study functional morphology. This is the evolution of usable structures. I guess the most simplest explanation or example of this one would be animals that typically eat meat have sharp teeth and sharp claws. Animals that eat plants have teeth better adapted to grinding and shearing of plant material. But this can also be expanded into muscle attachments on limb bones. It can be cranial ornamentation on animals and what were those structures used for. So pretty much just looking for the function of different parts of organisms' bodies. So that's something that paleontologists also study. We also look at growth and form, which we call ontogeny and comparative anatomy. So ontogeny is how you grow. It's how an organism actually grows up from juvenile to adulthood. So look back at baby pictures of yourself and then look at a mirror. You probably look pretty different. That's because you have undergone ontogeny. So we study ontogeny of fossil organisms to teach us about how these organisms grew up. And some paleontologists actually study evolutionary theory. Now, I want to point out that they're usually not arguing about whether evolution happens or not. We have a pretty good handle on that. We're going to talk more about that here in a few minutes. What they're studying are the modes and patterns and rates and causes of evolution and different philosophies on how to classify the organisms that we're studying to understand their evolutionary relationships. So they're really debating and studying the nuts and bolts and details of evolution, not specifically because it's been done so often and it's been confirmed repeatedly that yes, this is a process that's happening, but let's dive into the particulars on how. But I want to mention something else about ontogeny for a minute. Because again, ontogeny are the changes that an individual organism undergoes during growth and development. And this is important because when we talk about evolution here in a few minutes, there's going to be some comparisons. But here's why ontogeny is so important for paleontology. Let's look at the life cycle of a frog, for example, today. Something most of us know about going back to grade school, that frogs lay eggs in the water, the eggs hatch into little tadpoles, little fish-like organisms, and then as the tadpole gets bigger, it metamorphoses into a frog. That is an ontogenetic sequence. Now, if you knew nothing about frog ontogeny, and somebody showed you a tadpole or a frog and said, do you think these are the same type of animal? You'd probably say no, because they look drastically different. But if you know something about how tadpoles and frogs grow, you'd know that, yeah, you're looking at the same species, just at different stages in their life. Now, let's look at dinosaurs. Dinosaurs underwent some pretty extreme ontogeny in some cases, where going from a little baby triceratops here all the way to a big adult, we see quite a lot of changes happening. Look at the back of the skull, look at the morphology of the horns, the lengthening of the face. This is pretty extreme ontogeny. And there are some hypotheses that suggest that Triceratops E, where I underlined, is not even the last form, that perhaps their skulls grew even longer and modified even more. And there's some people that debate that aspect as well. So ontogeny is very important, because what you don't want to do is find fossil A and fossil E and call them two separate species when they're really the same thing, just at different ages in their growth cycle. But getting back to the paleontologists that study evolutionary theory, one of the things they do is they study taxonomy. Taxonomy, not to be confused with taphonomy, is the formal classification of organisms. It's how we categorize what organisms are related to who. You're probably familiar, at least somewhat, with this classification system: the kingdom, phylum, class, order, family, genus, species, or as I like to think of it, keeping precious creatures organized for grumpy scientists. This is known as the Linnaean system. It was developed by Swiss botanist Carolus Linnaeus. And essentially what it does is it takes two organisms and counts how similar their features are, how many features they both have. And the more features they have, they share, the closer they're related to each other. And in many cases, the Linnaean system works pretty well. So you have species, which is the most specific form, and you have a couple of species that make up a genus. You have a few different genera in a family, a couple of families in an order. There'll be a couple orders in a class, a few classes in a phylum, and a number of phylum make up kingdoms. Okay, so kingdom is the most inclusive group that we can think of in this. And we haven't completely abandoned this, but there are some problems with the Linnaean system. For example, a lot of it depends on what the individual researcher is focusing on. So I could be studying organisms that have wings, vertebrates that have wings, and I might put pterosaurs, even though they're extinct, bats and birds all in the same category, saying they're related to each other. And that's actually not very accurate. They all evolved flight, but they did so independently. So we have to be very careful when using the Linnaean system, because sometimes it just doesn't work. And in the past, people have kind of forced some of these organisms into these categories and boxes when they really didn't work that way. One part of the Linnaean system that we are definitely still using, though, is what we call the binomials. This is the way we describe a species. It has a genus name and a specific or species name. For example, if you go out to the woods and you see a coyote, coyote would be the common name. The binomial or scientific name would be Canis latrans. Canis being the genus, notice the first letter is capitalized. Latrans, the species name, is all lowercase, and notice the entire thing is italicized. So those are the three kind of steps in properly documenting a binomial or a scientific name. Now I want to point out, let's say you went walking in the woods and you came across a wolf. Well, that's the same genus as a coyote. They're both of the genus Canis. The difference would be latrans versus lupus, which is wolf, latrans is coyote. So wolves and coyotes are the same genus, they're different species. Homo sapiens are modern humans, but we could compare that with Homo habilis or Homo erectus from a few million years ago. We have the same genus name of Homo, but we have different species. Now, when we deal with fossil organisms like Tyrannosaurus rex, we don't have a common name. You might be thinking, well, what about T-Rex? Well, that's an abbreviation. We could abbreviate all of these scientific names. We could say C. latrans, C. lupus, or H. sapiens. So we don't really do that, though, with, we don't have a common name for our fossil organisms, so we can sometimes just abbreviate it from Tyrannosaurus rex to T-Rex just to save you time in typing. And that would be phylogenetics, or sometimes called cladistics. You might look at this family tree and go, that kind of looks like a person's family tree if we were to change all those names. So if you've ever played around on something like Ancestry.com, doing genealogy, or know somebody who has, you'll end up with a family tree kind of like this, where it branches and then branches and then branches, because that's really what evolution does anyway. That's what life does. So the way this works is it's different than the Linnaean system, because the Linnaean system just takes all the similarities between organisms and it says, well, which ones have the most similarities? That must mean they're closer related. And sometimes that works and sometimes it doesn't. But with phylogenetics or cladistics, you're not just looking at similarities. You're looking at where those similarities came from. So it's an ancestor to descendant relationship. So for example, if we look at this entire tree and notice where crocodiles and birds are, okay, so I will highlight those real quick. So here's our crocodiles and here's our birds. Now, those may not have a lot of similarities when you just visualize a crocodile and a bird. One is scaly and big and one's covered in feathers and they tend to be small. However, if you look at their internal anatomy and you look at fossil crocodiles and fossil birds, you find that they share enough characteristics to be called archosaurs. And this is actually where our dinosaurs come in too. Now, over here, and I'll do this in a different color, we have our snakes and lizards, a different group of reptiles. Okay. Snakes and lizards share quite a lot of characteristics with each other, and they only share a few characteristics with archosaurs. But when we look at the fossil record, we can see where the snake-lizard group went one way, and we can see where the archosaur group went the other way. And the one that's kind of right down there in the middle, or at their base, is the group Diapsida. So what this means is your cladistic analysis isn't just saying, well, these share characteristics, so they're related. It's saying they share characteristics that they all got from a common ancestor. Okay, so for example, everything on this tree is a vertebrate, right down here at the bottom. Fish are vertebrates. Amphibians, snakes, lizards, crocs, birds, and mammals, all of them are vertebrates. A vertebrate is an organism that has bones and a backbone. A tetrapod is an organism that has 4 limbs and lives on land, at least most of the time, or it had ancestors that had those characteristics. Notice that includes amphibians, snakes and lizards, crocs, birds, and mammals. Again, snakes, you're saying, don't have legs. No, but their ancestors did, based on fossils. Fish never had legs, at least not the way that we think of legs. So we would exclude perch and catfish and goldfish from our group Tetrapodus. But tetrapod includes amphibians, snakes, lizards, birds, crocs, and mammals. Then we get to amniotes. Amniotes are organisms that lay eggs on land. That would exclude amphibians. But snakes, lizards, crocs, birds, and mammals all lay eggs or give live birth. So this is how the phylogenetic system works, is we have to include what we know about the ancestors of our modern organisms. And this is actually codable. You can count up characteristics and give it a 1 or a 0 based on ancestor to descendant relationship, and actually quantify scientifically with math how closely related some of these organisms are. However, each one of these trees is a hypothesis. It is able to be modified with further data. So every time a new fossil organism is found and they plug in that information onto the tree changes. So these trees are working hypotheses. And when you have a tree where you plug in more data and it stays the same, that's confirmation. That is continued support for that, what we call topology, that structure of the tree and that evolutionary relationship hypothesis. Now that we've talked a bit about the basic principles of stratigraphy, and we've talked about fossils and fossilization and the importance of interpreting ancient life, we're going to kind of bring those together next week, where we are going to spend our lecture time looking at the concept and theory of evolution, which some have called the greatest show on Earth. Now, I look forward to seeing everybody in lab this week. Make sure that you read through the reading material for lab, work on the pre-lab assignment before you come to class. Make sure you're ready to go as soon as you get to lab, so we can keep socially distancing and kind of keep people coming and going without spending too much time in the lab itself. And by all means, if you have any questions, please feel free to ask me via email, stop by my office hours, get a hold of me somehow as soon as you can, and I'll be happy to help you out. Thanks.